Suzanne van der Put, a young Belgian mother, gave birth to a daughter without arms, then killed her. The Assize Court of Liège absolved her of the charge of infanticide. Public opinion all over the world seemed to agree with the verdict. This is the Rue des Lys.
These tragic birth defects in the 1950s and 60s were due to a drug called thalidomide. To understand stereoisomerism, first of all need to study the concept of optical isomerism, which follows next. In this video, we're going to look at what makes molecules optically active, what is meant by plain polarised light, and how do you actually draw enantiomers. Finally, we'll look at the story of the tragedy of thalidomide and how it can be avoided and how the drug has been remastered as an important anti-cancer drug.
Optical isomerism. Organic compounds containing a carbon atom to which 4 different atoms or groups of atoms are attached are called chiral compounds. A mirror image of a chiral compound cannot be superimposed on the original. It is called an optical isomer. These isomers have identical melting and boiling temperatures, densities and solubilities. However, they differ in their chemical reactivity. Optical isomers are sometimes called right or left-handed because hands are also mirror images which cannot be superimposed. In biochemistry, nearly all amino acids are chiral, and therefore any proteins, hormones and enzymes derived from amino acids are also chiral. This amino acid is alanine. The hydrogen atom, a methyl group, an amino group, and a carboxylic acid group attached to the same chiral carbon atom. Alanine has 1 chiral carbon atom and therefore just 2 possible optical isomers. More complex biological compounds may...
Molecules which are mirror images of each other are called enantiomers. In this next section, the lady with the very posh voice will explain to you what is meant by plain polarised light. The instrument that's shown is something called a polarimeter. Inside the polarimeter, the glass tube, your dissolved sample, is placed in solution and the plain polarised light is passed through your solution.
A beam of light is composed of electromagnetic waves that vibrate in all possible directions perpendicular to its path. Certain materials, such as plastic Polaroid film, have the property of absorbing all the waves except one that vibrates in a particular plane. Light that consists of waves vibrating in only one plane is referred to as plane polarized. Chiral compounds interact with plane polarized light, rotating its vibration plane to the left or the right. Therefore, they are referred to as optically active compounds. 2 enantiomers of the same compound will rotate the plane of polarization through the same angle, but in opposite directions.
In this next section, I'm going to show you how to draw optical isomers. You will also be shown how to draw the 2 mirror images in 3 dimensions. In this part, we're going to look at how to find the chiral centre, or the centre of a symmetry, and how to draw the 2 forms. So the chiral centre is also known as the centre of a symmetry because this is where the carbon has 4 different groups attached. Now the first thing to do, we're looking here at 2-hydroxypropanoic acid. First step is to draw out the full displayed structure. The next step is to then take this structure and draw the structure in 3 dimensions showing the tetrahedral arrangement of the atoms. So we've taken the central carbon here and the bonds now are arranged in a tetrahedral arrangement. Each bond is 109.5 degrees apart from each other. So what we do first of all is we take the carbon and draw that first. So I'm now going to draw a line here, and this represents the mirror plane. So imagine the molecule is looking at itself in the mirror and we're seeing its mirror image. So first of all, let's look at the central atom, which is carbon. So we're going to reflect the carbon atom here. The next atom I'm going to reflect is the hydrogen atom, and therefore we're going to draw the hydrogen atom here. So we've taken the hydrogen and the carbon, and now I've taken the carboxylic acid group and I've drawn the carboxylic acid group here. So what we're now going to do for the mirror image is we're going to take this, the carbon and the hydrogen and the carboxylic acid group here are all in the same plane. So we're drawing that there. The next group I'm going to take is this methyl group. So this wedge shows the methyl group coming out of the plane. So it's using perspective. So the methyl group is sticking out at you, and that's why we have this wedge bond here. Now, if you had a three-dimensional model, if you picked a model up and held it, you wouldn't be able to see the OH group. So what we do is use a dotted line, because that's hidden behind the CH3 group. So that goes here, and again that is reflected in the mirror. So notice the carbon has got 4 different groups attached to the central atom. And when a molecule has got 4 different groups attached to a central atom, it's completely asymmetrical, so it has mirror images. And we call those mirror images the enantiomers. So in this example, what we're going to ask you to do is draw the enantiomeric forms of the following molecules, showing the chiral centre with an asterisk. So first off, we've got 2-aminopropanoic acid. So the first thing is we draw out the full displayed structure, and we can identify the chiral centre here because this is attached to 1, 2, 3, 4 different groups. So again, we identify the 4 different groups, and then we start to draw the structure. So now I'm going to do the mirror image of this molecule here. So we'll start off with our chiral carbon here, and you can choose these in any order. I always tend to put my hydrogen at the top. Reflecting the carboxylic acid group here, it's in the same plane on the paper as the hydrogen is the carboxylic acid group. So I'm just going to draw that. You don't need to do mirror writing. So this is the carboxylic acid group reflecting. Coming out of the page, I've drawn the amino group here, the amine group. So that's coming out of the page. And then hidden sneakily behind is this little methyl group. So we draw a dotted line showing the methyl group going behind here. So these are the 2 enantiomers of 2-aminopropanoic acid. So on the next page, I'm going to look at butan-2-ol. With our butan-2-ol, when you draw out the full structure, you can see that the carbon number 2 has got a methyl group, a hydrogen, a hydroxyl group, and then this ethyl group here. So this carbon is the centre of asymmetry. So let's now draw the structures in the tetrahedral arrangement. So I'm going to take you through this process. So what we do first of all is we draw our central carbon atom, And then we draw the tetrahedral arrangement. Two bonds in the same plane, one coming out and one hidden behind. And then we draw our mirror plane, and we draw the mirror image of that tetrahedron, two bonds in the same plane reflected, one bond coming out at us, and then a group hidden behind. And what we now do is go to the main structure. I always put my hydrogen at the top if there is one, and then tick it. Got rid of that atom. Let's select another group, doesn't matter which one, I'm going to go for the OH. So if I put the OH group here, I'm now going to reflect it in the mirror here. Now we've got this methyl group and an ethyl group here, so I'm now going to summarise that as CH3 and this as CH2, CH3 to save time. So there's our ethyl group, CH2, CH3, and I'm going to draw its mirror image here, CH2, CH3. Remember, you don't need to do mirror writing. We've got rid of that. And now there's our methyl group. So that's going to be reflected. CH3 there, H3C there. So these are the two enantiomers of butan-2-ol, and this carbon here is the centre of symmetry, or the chiral centre. Now we're going to do the 2-amino 2-hydroxy butanoic acid, and again let's identify the chiral centre. So here is our amino group on position 2, here's our hydroxy group on position 2, here's our carboxylic acid group, and here is an ethyl group. So clearly the central carbon is carbon number 2. So all that remains now is to draw our two tetrahedra. And again, I'll walk you through drawing your tetrahedra. So there's the central carbons. Here is the mirror plane. These two groups are in the same plane at 109.5 degrees. Here's a group coming out at you, showing the perspective with this wedge. And hidden behind the wedge is another group. We've identified our 4 groups, so let's have a group sticking on the top. I'm going to go for the OH, doesn't matter which one. So if we've got an OH on this carbon, make sure the carbon's bonded to the oxygen. There's the mirror image of the OH group. Next, let's take the NH2. I'm going to pop it there, our amino group. So here's its reflection in this image here. Let's get rid of that. Now we've got a CH3CH2 group here. I'm going to put that here, CH3CH2, and therefore that is going to be reflected on the wedge here. And finally, what's left over is the carboxylic acid group, and again I'm going to summarise that as COOH. So if we have that here as COOH, it's going to be HOOC. So these are the two enantiomers of 2-amino 2-hydroxy butanoic acid. So the final molecule we're going to look at is 2-hydroxypropane nitrile. Let's identify the chiral centre. Well, when you come to draw a nitrile, make sure you show the carbon triple bond nitrogen as your nitrile group. So on position 2, we have a hydroxyl group, we have a nitrile group, we have a hydrogen, and we have a methyl group. So clearly the centre of a symmetry is carbon number 2. So now let's go and draw our tetrahedra. So now we have 2 groups in the same plane. We have a group coming out and a group coming out, one hidden behind the wedge group coming out. And now we select our groups. So as usual, I just like putting my hydrogen at the top. Doesn't matter where it goes as long as it's reflected. Let's select another one. Let's go for the OH. That can go anywhere. I'm going to put it here. HOOH. Let's put my nitrile group here. C triple bond N. C, make sure it's the carbon to carbon bond. N triple bond C. So make sure you always draw your full nitrile group and the OH bond, the covalent bond between your oxygen and your hydrogen. And finally we've got this CH3 group at the back here. Remember, it's carbon to carbon. Make sure this bond is joined to the carbon atom. Here is the chiral centre, and these are the mirror images or the enantiomers. These are the two enantiomers of 2-hydroxypropane nitrile, rotating plane polarised light in different directions. An equimolar mixture of both enantiomers will result in no optical isomerism, and the mixture is called a racemate.
This is the story of the thalidomide tragedy, which occurred in the late 1950s. What occurred highlights the importance of stereochemistry. Approximately 90% of pregnant women generally display some form of morning sickness. By the mid-1950s, thalidomide was being marketed and prescribed around the world, including Australia and New Zealand, to alleviate morning sickness in pregnant women. Although thalidomide effectively suppressed morning sickness symptoms, the drug caused severe and adverse birth defects. The first birth defect was reported in 1956. Making headlines around the world, the drug was withdrawn from sale. Australia ceased sales in 1961. It was the Australian obstetrician William McBride and a German paediatrician, Widukind Lentz, who suspected a link between birth defects and the drug in the 1960s. Here is the three-dimensional structure of thalidomide, which contains a single chiral carbon. A chiral carbon is one that contains 4 different groups. The presence of a single chiral centre leads to 2 possible enantiomers. Enantiomers are non-superimposable mirror images. While R-thalidomide alleviates morning sickness, it was later discovered that the birth defects were caused by the presence of S-thalidomide. In the body, the drug thalidomide is racemic. Thalidomide was used as a mixture of the 2 enantiomers, but even if it had been used as just the single R enantiomer, birth defects would still have occurred, as the 2 isomers rapidly interconvert in the body to a 50% mixture of both R and S thalidomide. The failure to understand this fundamental chemical conversion meant that it was never possible to solely administer R-thalidomide to suppress morning sickness. In 2014, the Victorian Supreme Court signed off on an $89 million class action for the victims affected by thalidomide in Australia and New Zealand. To protect the community from another thalidomide tragedy, the Australian government established the Therapeutic Goods Administration to regulate and control drug use and development. Today, thalidomide is tightly regulated and is being used in anti-cancer therapy. It carries a clear warning stating that even a single dose can cause birth defects.